Okay. I'm supposedly recording. Okay. So we're diving into chapter 6 today, and we may spill into chapter 7 a little bit. So chapter 6 is kind of light in my estimation. I'm working on redoing the homework because it's kind of silly. It's kind of silly. Chapter 7, which is what we're going to get to next week, I recommend not missing because it's really important. Like next week is what we're getting in, next lecture we're getting into K-maps, which is really kind of the heart of digital design. For this time, we're going to kind of step back and talk a little bit about logic chips. Now, some of this is going to be easy for you guys because you've already been working with logic chips in these labs, right? So we're going to hopefully clear up some of the mystery that may be confusing you guys. Hopefully you're not confused because in general, it's not too complicated. Sometimes it's just a vocabulary issue, right? So I've had you guys call up data sheets before, and that's just a sheet of paper, now PDF only universally, where you can figure out the properties of a device. And it'll be like the rise time on this switch is, it takes 5 nanoseconds to go from low to high in 5 nanoseconds, right? And so on and so forth. But one of the things that you'll notice is that you'll have part names that seem a little bit weird until you're familiar with them. And they have a long history, which is why they end up being, I don't know, almost arcane, right? When you start looking at this. So this is a part number, and it has different meanings to things. And all it's saying, this 74 is commercial grade. They use 54 if it's military grade. Now there's historic reasons for that, but we won't dive into it because it's not really important. It's just kind of familiarizing yourself with some of the parts. So we use mostly 74 because it costs more to use military grade, right? Because those are going to be shielded and radiation hardened. Because if you're flying in an F-16 and then the EMP goes off, you don't want your airplane to fall out of the sky. If an EMP goes off and your breadboard fails, nobody really cares. The LS is the logic family. So the same company might make multiple chips with different logic families. So if you pulled up your chapter 6, there's this nice little table, and the LS family is the low power Schottky logic. And all that's saying is what type of logic? Is it 5 volt, 3.3 volt? There's usually some attached speed limitations to it. Some of them will have assumptions of active high versus active low. So that's all the LS is saying is its type. 04 then is the device number. Most of the time that's going to be like the number of whatever devices you're working with. So if you're doing inverters, it might have a 04 in there for being inverters. It would have 4 inverters on it. Lastly, the N is just the, trying to think about how to phrase this. It's the package, right? It's what the plastic bits are containing, what plastic bits are containing all of the actual digital logic. So the N is what we're using, which is parts designed to plug into breadboards, right? They're the DIP. So there's a couple different ways. The ones we're using, this isn't just a count of the devices. They're actually using this as the device type. So your 00s are inverters, right? Your 0, what did we use last time?
04 was the inverter.
Oh, 04 is inverters and 00 is NAND?
Yeah.
Okay. Yeah. So sometimes you'll see another term in here. Sorry, it would actually go here. So it'd be like 0004 or 0404 to say that you have 4 of this type of thing. So really, for now, focus primarily on not having the count in the device. You can just worry about the device type. There's going to be some silly homework questions around that. Not too big of a deal. If you see a DIP, right, you'll hear the term DIP switch a lot. DIP is just dual inline package, and it's something, there's 2 lines, they're inline, and they're designed to plug into a breadboard. That's it. There's a list of various components, which I don't expect you to memorize at all, because that's a waste of time. But there is some terminology that we need to start addressing, just so that we're on the same page. So let's say we have this circuit. Yes.
So would the 54 and 74 series chips be like functionally identical?
Yes.
Like the same size, so you can prototype with the 74 and then
yes,
swap out.
Yep. Yep. Yeah, they're swappable packages, and in fact, companies will usually also design them to be compatible packages. So like if you went out and bought an analog devices 4-input mux, right? So a mux is just a switching device, has 4 inputs, and it just chooses one. So it would have, these would be the selection bits, A and B. And so if I selected 0, 0, it would connect this output to the, or this input to the output. And you can, so that's how you control it. So that's a mux. And if you went out and you bought one of these from Analog Devices, and it comes in a, well, we know we need at least 4 pins for the input, 1 for the output, and 2 for power, right? So we've got 7 pins, so it probably comes in an 8-pin package. Almost all of them are going to do this with VCC here and ground there. And then some, oh wait, sorry, I forgot those 2. It needs more pins than that. And then these 2 are probably going to be A and B. Anyways, I'd have to look up the exact one. But if you bought this from Analog Devices and you design your breadboard that way, and then Analog Devices went out of business, which is unlikely, but it could, and then you went and bought from like Maxim Integrated or Linear Technology, you could just throw the same part in there. They're going to try really hard to make them hot swappable, is what they're going to call it. So you just pull it in, throw it out. It still works because they want their salespeople to be able to come to you and try to sell the component, and they don't want you to say like, well, yeah, but then I have to redesign that whole circuit. And they're like, no, you don't. You can just trade it out, and ours is better. So, yeah, they're pretty much interchangeable. It's not always true. Some of them they try and rework. They're better for some reason, but okay. So here's a pretty simple logic diagram, right? We know that these are OR gates. We know that that's an AND gate, and we can figure out what the we could figure out what the function of this is. Well, hopefully you can, right? And what's more, we want to be able to talk about this in both this abstracted term and more specifically to if you turn it into a physical device. So we have something called designators, where you're going to start labeling them as, oh, sorry, and this has a bubble, as whether they're the same part or not. So let's say I take my first chip, and it has, say, 4 NOR gates in it. Well, I'm going to label my first chip U1. But it has 4 devices in it, so this is going to be U1A, U1B, and U1C. This is what we call the designator. This obviously is some different circuit. Oh wait, no it's not, right? Because this is also a NOR gate. It's just run differently. So we can now have U1B, right? If I had a second device that I was plugging into, I would then start calling it U2 something, right? Designator, important terminology. The wires that connect them together, we've gone over before, these are nets, right? On the output, you'll start seeing flags. That's a port. So something that they'll do if you're working with a real schematic is in the device, they would go to U1A, the first one, and they would add explicit power and ground symbols. So that you could then say this is attached to VCC. And then you might, somewhere else over here, do this. So because this VC is the same as this VC, they are connected together. So that's what's called a logical net, or a logical connection. It's not physically connected together, but they have the same name, so we know they're connected together. And we know that this is 5 volts because 0 plus 5 is 5. You can do the same thing. So let's say I wanted this net 1. And I was drawing another schematic that was using it. So there's 2 different ways that you'll see it. If it is in the same schematic, so on the same paper, I don't need the port. I would just write net 1, right? And because this one is named net 1 and that one is named net 1, they are connected. If this was on a different sheet of paper, I would add a port there and a port here. And that would let the schematic know, or you, the person looking at the schematic more specifically, that you can expect to find this net somewhere else on a different sheet. There is a concept that this goes about in a roundabout way. So I want you to be aware, I will say this explicitly. I'm going about chapter 6 in a different way. So you can read chapter 6, you'll get more information than what I'm telling you. I'm kind of squeezing it down to what's really important to you. So you'll notice, if you recall, our devices were using the LS family of logic. Those are really useful to stick in the same family when you're building a circuit. It's not always possible. You can use what's called a logic level shifter that will take, well, let's call it just a black box. It's going to have 2 different powers. It'll have VCC1, VCC2, some common ground usually. It might have separated grounds, but and then an input and an output. And this may be 0 to 3.3 for VCC1, and then VCC2 may be 5 volts. And so then it's going to step it from 0 to 5 volts. That's generally how you would transition them. But you may notice that in some of these logic families, you can actually just plug them together. So like the LS and LV, the low power Schottky and low voltage, they're slightly different logic families. But even though that's true, a lot of the times the 3.3 input, say, so if I'm inputting a 3.3 volt into a 5 volt, that 5 volt may swap over at 1 volt. So I don't actually have to go all the way to 5 to trigger it. But I do need to go all the way back to 0 to go back to 0, right? And so I could plug that in, but I can't go the other way because if I put 5 volts into a 3.3 volt, you're liable to break it. There are other problems with doing a 3.3 to 5, so we try and use the level shifters. Mostly in that we'll actually get into some of the delays in a bit, but the delay between asserting the signal at the input and the signal coming out of the output is dependent upon the input logic level. So it will slow down your circuit to do it that way, rather than having a level shifter. Okay, I'm gonna leave this up here for a second. And if I start, so I need to do this. For anybody watching the video, I apologize. I think anything over here is unviewable. Yeah. So what I drew off screen is just this. Really? Is this off screen?
Just a little.
Okay. Sorry. So this gate just has a net plugging into it if you're viewing this. The other thing that I drew off screen was a power supply logical net that just looks like so. Okay, that's for you viewing at home. Okay, something to be aware of. We've covered it a little bit, but I want to call it out explicitly. If I'm limited to 2 input NAND gates, how do I make a 4 input AND gate from just 2 input AND gates? Right? This is now a 4 input AND gate. Because the logic expression for AND, A, B, C, D, A and B is the output here, right? So I can label my nets for what they are logically. And this is C and D. But now I've just had A and B and C and D. But I didn't change anything, right? That's the same logic expression. Similarly, OR gates we have A or B, C or D, and now we're just saying A or B or C or D. But notice that the parentheses don't change the summation. So that this is a 4 input OR gate from just 2 input OR gates. To do a 4 input NOR gate, it's just that. I take 2 ORs, throw it on a NOR. The challenge then is you may need or if you only have NORs and inverters, you may need to do NOR, NOR, invert, invert, NOR, right? Obnoxious, but doable. ANDs and NANDs are the same way. You just invert the output and use ANDs there. So you only need to invert the output 1 time. Yeah. Make sure I don't miss anything. So the book calls out, and it's probably worth mentioning, that using the parentheses doesn't change anything, but it's useful to do sometimes when you have this logic expression to help yourself think through what you need. Like, oh, I only have, so I end up with an expression of like f equals ABC or, right? I have f equals ABC or ABD. I may start adding parentheses to be like, well, I only have 2 input AND gates. So I'm going to do an A and B and a not A and B as one of those inputs, and then the OR gate is just going to stick those together, right? So using parentheses to explicitly pair things together without changing the function is a good way if you're not quite sure how to build it in logic. So I'm going to just ask, if I gave you nothing but I don't know. I mean, if I gave you nothing but ANDs and OR gates to use, I assume you could all draw this out really quickly, right? But you would also need to be able to do this using NANDs and NORs. And that one's a little bit more difficult, but that goes back to either the 2 methods we've talked at before, right? Which is the bubble pushing method that I've talked about, or the, I can't remember what they call it in the book, for the books method, which either way is just about adding bubbles. So drawing up the gates as you would expect them to be, more or less, always starting with the output gate, right? But in this case, our output gate, what is our output gate in this function? OR. Yeah, because it's ORing 1, 2, 3, 4 terms. But there's a problem with that because I now have a 4 input OR gate, right? And what if I only have 2 input NOR gates? Well, that can start getting difficult. Because I know that to do that, okay, now that's my output gate. But I need to make this into NORs or NANDs, right? So NORs or NANDs are universal gates. That also means you can use them to build any other type of logic. NORs and NANDs are also useful because they're minimal circuit requirement gates, meaning that they both only need 4 gates. So they're very useful to have. And if you recall, you can have a situation where your logic expression, if you start with an OR gate, it's very easy to go into NAND gates, right? Because all I have to do is invert this input, invert that. Now we're a NAND. But I've inverted things, so now I have to move some bubbles. So now I'm going to invert and then de-invert. So this is the same expression, but now we have NANDs and NORs. We're good, right? Everybody's happy. And then we can continue on building these. You guys think you could build the rest of the circuit out with NANDs and NORs if you had to? Right, so just a quick, each of these input is going to be a 2 input AND gate, but you have to turn that AND gate into a NAND or NOR, which you can do by inverting the inputs, right, is probably the easiest way to do that. Because the other issue is you can also do that, but then you need an inverter here. Right? I don't just want to draw a bubble here, because then I have bubble, 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 and it's not really a NAND or a NOR. It's kind of some quasi weird thing. So it's better to explicitly call it the inverter. So that's how you design that circuit to get it into universal gates.
Here's the anniversary of it.
Okay. So there's this next term, this is switching gears a little bit, called propagation delay. And all that's saying is, let's do it a simple way. If I have an inverter and my input in, out, goes like so, right? In an ideal world, the output would start high and go low, right? But what really happens is that these circuits are not instantaneous. There is some delay, and we call that propagation delay. So this switches at the input, and after some amount of time, I guess I can draw this solid since it's different color, it's going to switch. That delay is what we call propagation delay. You will find propagation delay in the data sheet, which we've talked about before, and it's going to be defined as time propagation high low, or time propagation low high. TPLH, TPHL. So the time propagation from high to low. And that is the, I will apologize dramatically if I'm wrong, but that is what, that description is what's happening to the input. A couple things that you need to be aware of with the propagation delay is it is dependent upon a couple of things. It is dependent upon the number of devices connected at its output. So you'll see it as CL equals 50 picofarads. So that's saying you will get some propagation delay, whatever I say. So say this equals 3.3 nanoseconds. It'll be defined at 3.3 nanoseconds if the load is 50 picofarads or less, and the temperature is 25 degrees Celsius. If the temperature goes up or the load goes up, you may get worse performance than what they promise in the data sheet. This time won't be defined just as 3.3 nanoseconds, however. It will be defined with a min, a typical, and a max. So it might have a minimum 3.3. Typically it goes about 4, but if you got a bad device, it might take as long as 5. Right? Because propagation delay is bad. We want 0. Farads. You may not be familiar with this yet if you haven't taken 1270. Who here hasn't taken 1270? Taking, okay. So farad comes from capacitance. A capacitor is drawn like so. A capacitor is just a device that stores charge. So I can put a ground here, and I could put charge across this. It might have some voltage across it, not dissimilar from a battery. If you're an audio geek, you're probably familiar with capacitors because they put them at the power supply. Because when a bass, for example, hits really hard, it draws a lot of current. It needs to pull that current from somewhere, and your battery, like in your car, say, may not be enough to drive all of that current. So what you do is you install a capacitor alongside your battery, and when a lot of current is drawn, it can pull both from the capacitor and from the from the battery and the capacitor, which allows for more total current. However, the reverse is true, that it also requires more work then to charge this back up. So in the case of our circuits, if you're attached to a capacitor, it takes more work for this guy to switch. So if there's nothing there, it takes virtually no effort to go from 0 to 1. If there is a capacitor, it's going to be like, oh, we got to try and work harder for it. Because that capacitor needs to take that charge and store it up so it can be used later. These capacitors happen because if you looked at a gate at an input terminal, there is actually what we would call, that's a ground, parasitic capacitance. Ideally, they would have none, but capacitors are just formed by parallel plates of metal. So your device has sheets of metal in it, or silicon, right? And between those two, you create capacitance. You end up with parasitics. You'll delve into these parasitics in several of your classes, but that's what it's causing. So when you're doing that, you need to know how many devices that you can connect up to. Okay, almost skipped something. Back to the propagation delay just for a second. Something to keep in mind is if I were to put a signal in here at the input, the propagation delay from the input to the output is the sum of all of the propagation delays. Does that make sense? So what that means is your overall propagation delay of this circuit, so say that this is B0, B1, B2, B3, and B4. So say this was your final circuit. The total propagation delay at F is a result of the longest path, right? You don't really care necessarily yet, we will eventually, about the other propagation delays. What you care about first off is the longest path propagation. Now this can get a little confusing because you may have two paths of identical length that actually one takes longer than the other, because the propagation delay for an inverter is probably shorter than the propagation delay for a NAND gate. Because an inverter is only 2 gates, single stage, NAND gates, 4 gates, right? It probably takes a little bit longer for your NAND gate to change. So if we had something over here that had an AND gate, well, let's say just an AND gate and an AND gate, these paths are the same as far as number of gates, but this path is actually the longer path. But you would need to know what the propagation delays for each of those parts are to make that decision for sure. So the 3-step process in order for calculating the total propagation delay is identify your paths, figure out which ones are likely to be the longest, calculate them, and then pick the longest. That's your 3-step for figuring out your propagation delay. And it looks like I was correct when I said earlier that for inverters, for TP high to low, we care about the input. So if the input is going low to high, I use TLH, even though the output is the opposite of that. Another way, another vocabulary term for these delays is T high or low to high. Let's start with that. And I'm running out of space. Let me erase the numbers over there so they don't get too cluttered. What else can I erase? Let's get some simplifying done. Okay. Low to high is the assertion delay. And that's because we are asserting a signal. The high to low is the de-assertion delay, because we're unasserting it or de-asserting it. Okay, so let's say I've labeled my components, right? Given them designators, if you recall. The way that I would start planning out my propagation delay is I would say something like I have B0 and it goes to U1, it goes to U2, U3, U4, and F. Now, these two are just the ports, right? The ports themselves don't have any delay. So then you would go in here and start plugging in the propagation delays of each of these gates. So let's say we use that NOR gate and it's 3.3. Say the inverter is 1.0 because it's fast. The next, or sorry, NAND gate. Then this one, let's say, is a little bit slower. And then U4 is going to be the same as the previous one. Right, so you can look up what these propagation delays are, and these are all in nanoseconds. And then I would just sum up these delays, and that's my total propagation delay. But I would also have to do that for this path as well, to make sure what it is. There's going to be some homework assignments on that. It's pretty straightforward. There's an example, example 6.2, page number, because these don't have page numbers. That you can walk through is pretty obvious. But the one thing that they do there that I haven't covered so say I have a 4-component inverter. Meaning there are 4 inverters in a single component. And I'm doing something like B0 goes through an inverter and goes to F, right? Simple circuit. That means I have 3 other inverters that are just kind of hanging out there. What do I want to do with those inverters? Do I just want to leave the inputs hanging? That's what we've done before in the labs, right? Well, in the real circuit, you probably want to do something like this. Just ground the inputs. Or you could raise it up to power. It doesn't really matter because your major power consumption is from switching the inputs. That's called the dynamic power consumption. So anytime you're going from low to high, it's dynamic. If it's stagnant, it's your static power consumption. If these guys are staying high or low and have no load, that static power consumption is virtually nothing. But if these are floated at the input, some of you discovered this, right? You design circuits in the lab. So the ideal situation is we have like a switch, a resistor, and this is your output. But some of you didn't use this, what we call the pull down resistor, right? If you put it up here, it's the pull up resistor. You switch the order of that. If you don't use that pull down resistor, we know that it is, so let's break that connection and explicitly write VCC. In this case, we're broken. If the switch is closed, it is VCC. If the switch is open, it's something, and that can change. And so that can start randomly switching up and down on the output and creating unnecessary power consumption. And it could also introduce what we call switching noise, which can affect any other signals going on. So it's not desirable to leave random floating inputs. So we want to have explicitly call them down. For your lab circuits, it's probably not a big deal because it's not like it's, you have unlimited power, quote unquote, in there. And you're not particularly noise sensitive, so it's fine to not go through all the work of tying down those inputs. But be aware that that is the right thing to do if you have a finalized design. So we've talked about propagation delay, and previously we've talked about simplifying logic, right? So the thing is, there is this conflict between logic simplification and logic and propagation delay, where the simplest logic expression may not be the logic expression with the lowest propagation delay. The lowest propagation delay possible is either what we call the sum of products or product of sums. And you're going to hear this term a lot going forward because this is what is outputted by K-maps, which we'll get to next time. So sum of products just means I have a bunch of products and they are summed together, right? And so what this is showing is that it's only two gates, right? There's one OR gate and then one AND gate, no matter what path I take. All paths are equal, therefore minimized. Product of sums is just that, right? We have some sums that we multiply together. That gives us the AND gate output. Similarly, if we're trying to design a circuit, right, AND gates are easy to turn into NOR gates, and OR gates are easy to turn into NAND gates for conversion. And what's nice is every single circuit, every logic expression has an equivalent sum of product and product of sums. Every single logic expression can be expressed as product of sums or sum of products, every single one of them. So there is equivalence between them. You just have to find out what they are. And we'll give you tools to do that in the next lecture. I don't know why the book calls this out, but if you have an expression that is this is both a sum of product and product of sums. But it's just because that, if you're looking at this as a term of a product of sums, the sums are just A and B and C, right? There's nothing fancy. I don't know why they call it out, but I'm going to call it out for you because maybe you'll run into a problem that asks about that. Okay. Like I said, this course is not super, or this lecture is not super dense in material mathematically, but it has lots of terminology. Okay, so let's say I have one OR gate that is feeding into a bunch of AND gates. I didn't draw the other inputs on the AND gates, but this process of going from one output to multiple inputs is what we call fan out, right? It's fanning out to multiple connections. The fan out is what you're worried about when you start looking at the propagation delay and the load capacitance, that's CL. Because each one of these AND gates has some load capacitance, and so on and so forth. And so say this can drive 50 picofarads, and each one of these has 10 picofarads of capacitance, then I can only hook up 5 of them before I start running into problems. So I hook up the 6, and it's going to start slowing down my circuit. I will no longer have that guaranteed driving specification on the propagation delay. And if you get to too many of these, it may just break the circuit, to be honest. They just behave very weirdly. Because there's another issue that some of you have actually seen in labs as well, where in an ideal situation, these gates don't take in any current. But again, they're real devices. They do have current. And you're going to see the current labeled as so. Which is just I is current, right? So current in high, current in low. Current out high, current out low. And what that's saying is this is going to have some output current maximum. And these are all going to have input currents. And if the input currents exceed the output current, we're going to have a problem in this device. So if you have devices in the same logic family, well, let's go with the generalized form first. You need this requirement to be true. Where the, the input output current when low needs to be greater than the sum of all input low currents. Same is true if the IOH needs to be greater than the sum of IIH. And that's always true. If it's in the same family, if you have all the same devices, you can simplify that down so it just looks like IOL is greater than or equal to NIIL. Right, because I just have some number of devices that have a fixed IIL. So if you're doing the calculations, you just figure out all the devices that it's calculated to, add all of them up, and see if it's less than the output, right? Straightforward. There is in this section, sorry, right before section, right before the end of the chapter, actually, there is a, the equation is 6.10, this guy. Right after that, there is a description of capacitance. If you want to go read the book's take on its description, it goes about it describing it a little bit different way. So it goes on and say voltage is resulting from separating charge. Now that sounds a little bit weird, but all that's saying is if I have a resistor and current is flowing through it, some of the charge hangs out here and less of the charge is over there. I have separated the charge with the resistor. We call that voltage. Capacitors are going to do roughly the same thing as a resistor, but they have some different properties that you guys will get into more in 1270. I don't want you to worry about that in this class, but ultimately it talks about the farad, right? So I was talking about picofarads, right? And that's 10 to the negative 12 farads. A farad is, by definition, a coulomb, which is the unit of charge, per volt. So, coulomb per volt. Similarly, so I already covered this, went out of little order compared to the book, where, right, I have Cin, that's the input capacitance that we were talking about, and Cin, sorry, let me declutter the board a little bit and write somewhere else. This is another important equation. So in your data sheet, you need the specified CL to be greater than or equal to N times the Cin of your devices. Right? Pretty straightforward. You can rewrite that as N, the number of devices has to be less than the ratio of CL to Cn, which will come out to like 5 or something typically, right? Well, in the families that you're using, I think it's actually closer to 10 gates or something. But the nice thing is that you can always, if you need to drive more gates than that, so say I have this big fan out that goes to a whole bunch of devices, right? And each one of these is like an inverter or an AND gate, and so on and so forth. If that starts becoming a problem, instead of having this, I can group them into just a series of buffers. Now each of those buffers only has to drive, or even, right, so these are all tied together. One buffer drives these 3, and another buffer drives these 3. So if my N, say, was 3, I'm fine. But when the 6 was connected all up to one gate, so I had some OR gate over here that was initially driving all of them, disconnect that, branch it off into some buffers. Now this N is 2 and this N is 3 and everything is fine, right? So that's what buffers are useful for. You may only have inverters. Inverters are great buffers, but you have to just do it twice or adjust the logic down the line. So we've got 20 minutes left. Which is really good. So that's chapter 6. Homework for chapter 6, I think, will be delightfully easy. I hope. I'm going to start into K-maps. I'm going to go back over all of the K-maps next time, but it's because they are so important, and if you understand K-maps, your life will be easy. And if you don't, your life in this and in 3610 will be unpleasant. So this is chapter 7, and I say this, let me gather my thoughts and take a drink because my mouth is drying out. Okay, so I want to give you guys some history, right? and I may have discussed this before a little bit, in the olden days, you would have programmable logic that had a couple of devices. And by programmable logic, I mean you can just send it codes and it assembles itself into whatever logic you told it it needed to be. 3610 gets into the nuts and bolts of how this works. I don't want to worry about that. But the problem was that if you only had 20 devices, you really, really had to worry about optimizing your logic. Because if you didn't, you would run out of room on your device. Even 10 years ago, when I started down this path, FPGAs really had a room constraints problem all the time. Now FPGAs have gotten huge, and the problem's not really there anymore. Your main concern is like balancing how big your device is versus power. But the number of devices isn't really a problem. But if you go and work out in industry, you may encounter old devices, right? You may work on a manufacturing floor that has a control system driven by what we call a SPLD, or a simple programmable logic device. And that may only have 50 devices on it. And you need to be able to, A, understand how to derive or analyze what the circuit is doing, right? We've covered that in previous lectures. Once you do that, you may need to simplify it more, because you want to add functionality, say. And say you pull it out and it has 50 devices and it's using 42. But you want to add functionality and you're going to require 12 gates. So maybe you want to simplify that logic further. But the logic simplification can get really hard. So what we want to do is have a tool that allows us to simplify the logic, even if it's very complicated, quickly. The way we do that, one of the prominent tools for that simplification is called a Carnot map. I don't know how it's pronounced. We just say K-map, which is why I forget how it's pronounced. K-A-R-N-A-U-G-H. And what he started realizing is some kind of interesting patterns in the way that the logic related to each other. So he has this idea of logic adjacency. And that term itself is fairly loaded and fairly complicated until you start seeing it visually. And what that starts meaning in its simplest terms this logic, everything is adjacent to each other, right? So this is where the map starts. This is the most simple form of it, is I have two inputs, A, and it's either not A or A, and not B or B. And in the map, this term is not A, not B, and over here we have A, B, right? So you're gonna start seeing me draw lots of squares over the next lecture or two. And because of that, the logic here is, and I will probably delve into the reasoning behind it more later, because the reasoning is interesting, but what we do with it is useful. So what you do in a K-map, the function of a K-map, let's do 3 inputs now, because 3 inputs is just more useful as a demonstration tool. So if I have 3 inputs, right, I have 2 to the 3, so I have 8 different potential values. The way we do this is we label them like so. There are alternative labeling that you may see from time to time, like where they explicitly start drawing out A, B, or well, so here they would go not CC, like I did before, right? Or the way I like to do it is C is either 0 or 1, right? Those are equivalent. So this is not C and this is C. But I want you to be aware of both of those options. Now similarly, we're going to go over here, not A, not B. Not A, but B. But something interesting has to happen here. Because this, how we would normally count in binary, these are not what we call logically adjacent. Because if two of the numbers switch at this, two or more of the numbers switch at the same time, they are no longer logical neighbors. So what we do is we start using what we call grayscale or gray code, which, sorry, gray code is the right one, where now 0, 1 to 1, 1, only one term has changed. It is still logically adjacent, and now I can do the 1, 0, and it is still logically adjacent. What makes this even more interesting is this box and that box are also logically adjacent. So let's say we have a truth table, like so, that has three inputs, C, B, and A, and we're worried only about one output. And it's going to have something, sorry, I don't think the book gives me the truth table. They teach it a different way, but I'm going to keep pressing forward. Actually, this is might be an interesting learning experience. So they give me a truth table, not a truth table, sorry, a K-map that looks like so. Now, this seems arbitrary, but I want you to understand where it comes from. I can actually go from truth table to K-map or K-map to truth table. So if I look and they're all 0, 0, 0, 0, it is a 0. Similarly, if it's A, B, and not A, not B, but C, this guy, right? That guy is a 1 because it's a 1 in the map. 0, 1, 0, 0, 1, 0 is a 0. Turns out I probably should have written ABC the other way because of the way I drew the map. But, right, do you guys see how you can go in and fill in this whole truth table just using the K-map? And similarly, you can use the truth table to fill in the K-map. So if you only had a truth table, I could go 1, 0, 0. C is 1, and A and B are 0 is that one. It's a 1. Okay, so now I have a K-map. The K-map, this is where the tool starts coming in and getting useful and potentially confusing. So what the logic adjacency means is that if there are terms that are neighbors, we can start combining these into like terms. So if you recall from our truth tables, we can build sum of products from a truth table, right? So I could say something building off of this, F is true if not A, not B, not C, and let's find a different one as well. So this is not C, but A and B. So or, what did I say? Not C. Or so on and so forth, right? So I just write one or term for each of those. But what this is saying is if they are logically adjacent, that means those two terms are going to be able to simplify together. So let's simplify them in one step. And the way you do that is instead of having this one as a term and this one as a term, they're logically adjacent, we can now combine them into a single term. We do that by saying, okay, we've circled this. C does not change, right? Because it's horizontal. And A does not change, but B does change. So what that circle represents then is A, C bar. because C doesn't change and it's 0. A doesn't change and it's 1. Now, this is where the cool part comes in, because this and this are logically adjacent. I can have a circle that goes around the K-map. Yeah.
So can you do the same for max terms for the knots?
Yes, exactly. So what he's asking is about max terms. So these are, the ones are what we call min terms. Zeros in a truth table are max terms. You could circle zeros instead of ones. Well, let's keep with the ones for just a moment. 4, okay. So now we have these two ones. C is 1 and does not change. And A is 0, it does change, right? Because we go from 0 to 1. But B is 0 to 0. So now we know we have B and C, and we just have to figure out what it is. Well, C is C, we're good, and B is not B. Once we have all these ones circled, we're done. That's the expression. That's it. So we could have had 4 OR terms, each with 3 terms in it, right? Or we go right to that. How nice is that, right? For min terms, you can generate, and remember, so this is tying back into the propagation delay, where now I have also a minimized propagation delay because of the form of the expression. For min terms, we can also say, start circling the zeros, and I'm not going to go through that right now, but it would end up being a sum of products instead of a product of sums. It switches around. We'll get into that probably next time specifically. I'm going to call it 7 minutes early. That's not too bad. I want you guys to digest some of that K-map. I'll try and get homework 6 posted during my lunch hour so you guys can go look at that. I have noticed a thing. A lot of you guys wait till the very last minute on the homework. Try not to do that because I do have office hours and I think I'm helpful when you come to my office hours, but only 2 of you have ever done that. And you can also arrange Zoom office hours if you can't make it in that time. Mondays and Wednesdays are bad for me because I'm booked. Oh, yeah.
The alignment I figured out changes because if you have a reference length of 100 and your read length is 1, all the alignment is going to be repeated.
Yes, part 1 they were not. It
Is
was
it-
never 1, 2, and 3.
Exactly, because on part 1 it's such a small data set. You created it to follow that alignment, but as your reference length gets bigger, you notice the read length is staying the same. So it's just naturally going to fall down into more doubles. So that's what I found. Maybe I'm doing it wrong, but that's just I'm thinking about it. That's what
I think the line for number 2, it was using the part 3.
for part 3 took me forever. It took like 6 minutes for my program to run.
It was there at PM, it's like, yeah, then give up.
I need to get 7 real quick.
Yeah,
How long did it take your program to execute? To execute?
Kind of picking up your bag for me so I can spread this thing out. No.
Mine took way longer than 0.1 seconds, which was what it was supposed to be.
I think I was having an 80, maybe.
I hope.
You're doing a video,
Yep.
and then pass down, you know, be blurry, and then see.
I did it for chapters 1 and 3. It worked. Just gotta go slow, get the image, and then you just scroll through the video and get to this. Where you can read it.